the port list X in one integer. The actual signal in your circuit, right, will be mapped to your original design using this order. The same order. Not inverter. I call an instance of this one, right? And then this is the out one output. And then X is your actual input. Okay, done, right? Done. Okay? So this is actually showing that what? We can easily design a combinational circuit by using the primitives. Okay? Right? Now this is the internal right here. What primitives do we have? This is just some basic primitives. And OR gate, NOT gate, buffer, XOR, NAND, NOR, XOR, right? Plus the buffer if your enable is 1. This is the buffer, but with the enable. If enable is 1, then A equal to 1. Buffer if 0, buffer with the inverted enable. If enable is 0, A equals 1. Not if 1. You have inverter with the enable. If enable is 1, A becomes A bar equals 1. Not if 0. Inverter with the inverted enable. If your enable is 0, A becomes P bar equals 1. Those primitives are included in the library. We can directly use them. Okay, right? Now, primitive pins are expandable. For example, we have a NAND gate. Okay, so output 1, in 1, in 2. However, we can also expand it to 3 inputs, NAND 1, in 1, in 2, 3. Or even 4 inputs and many inputs, NAND 1, in 1, in 2, 3. Right, we can develop multiple input primitives. Now, let's look at a half-adder design. When we design a circuit in VERILOG, we have choices. Either describe the behavior model or as a structural model. Structural model, we let's say actually define what the components are there, how they are connected, that's very detailed. But the behavior model is a high abstract level. We just tell Alexa we want this function. How are we going to achieve this function? You have flexibility. So in the logic synthesis, different synthesis tool may come with different design, but both of them get the job done. So in this one, we said what? A behavior model is a higher abstract level than structural model. Right? Okay, this is just like what? I assign you a task. Okay, you are going to finish it in 10 days. And how you going to finish it? I don't care. What is it? Structure or behavior? That's a behavior, right? Behavior. Okay, I just need to get the job done. If I say that what? You first do this one, and you move this table to there, and move this table to there, I give you detailed description. Right? That's a structure. Okay, so you have very detailed connection with the structure and the connections. So this way, the behavior model is a higher abstract level. Now let's try to use a primitive to design this one, because we already have the base case. Then half-adder we can design in this way. Half-adder module name. We give a name. Everybody we have a name. Input output list. SC X1. And the input X and Y, because they are single bit, so we don't need to specify the bits. Output SC. Now XOR primitive with S X1 this game. And with this output, this input X1. Done. Easy, right? Is it easy? Okay, so we can use primitive to construct a circuit. just designate their input-output port list, but stick with the same order as your original definition. Okay? Now, this one, we define it as a name. In the future, we can easily instantiation, right? We call many instances of this half array. We don't have to repeat it again. Okay, that's the convenience. We just build one table, design one table. We can actually call many tables, and then we can quickly construct a classroom by connecting them together into the order we want. Now, a full adder design. Of course, we can also use primitive if we can figure out the detailed gates construction. Right? How should we do it? Following the same way. Module full adder, CR sum ABC. Input output wire, we have wire N1, N2, and this internal wires. And then we're going to call these primitives. I'm going to imagine. Okay, I'm going to hide this. Follow that example we showed you just now. Now, I'm going to put it back into here. Oops, sorry. This is the circuit we want. But we give you these examples in the bottom. Now, can you design this full adder? Let's do it together. The best way to learn is we try this with examples. Okay, good. I'm going to invite some students. Follow this example. Can you use primitive to design the full adder? I'm going to invite you to help us, right? Would you like to help us? Right? Step by step, we have example. Everybody, can you please take out your pen and paper? Let's quickly design this. Following the example, right? Following the example. You should give a name and then list all the output. And then define their directions and the length. Here is big. And then, yeah, so follow this example. Can you design this for us? So into a module, F or AD, and then output into the list. And then define the signals, and then what gates are there. We have internal wires, we call the wire N1, N2, N3. And then you call XOR gate, NAND gate, XOR gate, NAND gate, and specify their connections with the order, the same order you defined before, and then you know, output input. Right. This is the example we showed you. Can you design this circuit? Yeah, let's practice together, okay? And it's very helpful for us to understand how we can design a combinational circuit using primitives. Very easy. Declaration by module name, for the list, and then define the directions and the width of all the input-output ports, and then call the primitives. Specify the connections. How can we specify the connection? Using the same order for your original as a primitive design. And then declare their signals in connection in your circuit. Right, your circuit. We call that a table, and then put it here, and then connect each leg to your node. And then we actually, yeah, connect your table into this cluster. Yeah, very nice, very nice. Okay, A, B, C, all that is very good. and then you say XOR is N1 AB, right? And then NAND N2 AB, and then XOR S AB. This AB is not your here AB. It's at N1 N2, right? S N1 N2. Your actual signal maps into the original design by the template. Yeah, follow this example, and we can go to design. Design the more complicated combination. If we can design this combination, or we can design any combination. No secret. Very good. XOR, and another XOR is this one is S1 and 2. Oh no, not S1, S1 C. Yeah, you have another XOR, right? XOR is here, right? Then it's S, and then this is N1. And then this is actually a C input. So here we put A, B, that's your nominal input for your original case. S, N1, and C. Very nice, great job. And then we have another NAND instance, N3, yeah, NAND, and then N3, and N1, and C. The actual signal. I think you're this one is N3, and then N1, and C. Very good. And then we have another NAND with CO, N3, and N2. Yeah, let's do it together. Take out your pen and paper, and you can actually simulate this together for the stupid time. And then here, right? CO, N3, and C. Oh no, no, not C, N2. Very nice. Good job. And don't forget, in the module. Module in the module. Yeah. Congratulations. Good job. Right? What's your name, please? Isaba. Isaba, I'm so proud of you. Okay, good job, Isaba. I think Isaba did a wonderful job. I'm going to take a picture of Isaba's code, right? So you see? Isaba's code. I hope everybody has your own code. His question.
Do we have to declare a wire?
Oh yeah, we do need to declare wire as well. So we need to add another reason we can actually move it together. Can you add that wire? Add that wire. Okay? Because every signal has to be declared before you use it. So we add one more line, wire, N1, N2, and 3. Very nice. Good job. Congratulations. Then together, it's a complete code. Right? Okay, good. Now we'll see. What's the design? This is the code. I think our students, both students jointly, together, we get it done. It is actually like this. We declare the wires. And then with XOR, NAND, and 1. Good job. Congratulations, right? Isaba and good job, right? This is the design. Is this okay? It's easy, right? It's easy. Okay, good. That's a full added here. Now instantiation of the module. Once we already designed this a half adder, we can reuse it, call the instance, and then construct a full adder like this. Okay? So this way we're going to show you how can we call the instance. And see, that's your Isaba and another student will call it just now. We're going to recall it. We don't have to review it. And then when we recall it, we have to follow the same order of the instance. When you specify your actual signal in your circuit will follow the same order, right? Because otherwise they are swapped, right? Swapped, and that's going to cause error. Now, how can we do it? We're going to define module. We give a name F adder, full adder, right? SC XYZ, right? So XY is the two numbers you want to add. Z is your carrier. Now, how can we do it? How can we do it? We can actually use two half adder. The first two adder together get a sum. Again, add the Z. And then you get the final sum. How does it carry out? First two one, you all get together carry out. And then this another carry out. You have the actual carry out either from here or from here. And that's going to be the final carry out. Okay, we're going to use all data. Now for this circuit, how should we use the structural model to design with the instantiation? Again, first declare the module. The module name, and the port list, SC, XY, and define the wires, the ports, right? The direction. Input XYZ, output SC, but you have internal wires, W1, W2, WC. Now we are going to call two instances. So this way, the instance we call it what? The M1, M2. We give a name. M1, M2. Now, what are they? That's your original design. Make sure you use the same name. Okay? And then the instance we give a name. So this is the table. Then we can call instance table 1, table 2, table 3, table 4. They are the identical copy of the original table. So the way the original design M1. What is the connection? Follow the same order. Sum carry out X1. So in this case, W1, W2, X1. Max. This one map to this one. 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 1-to-1 correspondence. It is okay. All the matters. Another one, another instance here. M2. Again, follow this same order. S sum WC. W1, W2 for the input. Or W1 and Z, right? Z for this second for I. Plus another instance of your primitive. That's easy, you get it just now. Okay, of the C and the WC and W2. Done, right? End the module. Any question? Can you design a what? This is 1 bit, a full adder, right? Can you use this 1 bit full adder to design 4 bit full adder? See? Right? We can also challenge you. Example. Okay? 4 bit full adder. 4 bit full adder. We already designed a 1 bit full adder. Now, can you cascade them together? Then you need to call 4 instances. Right? And again, give a name. And this is the total in and out. Right? The port list. Each of them specified. But now, your A and B, each of them are 4-bit vectors. That's the reason with the bracket C down to 0. Out of the sum, also 4-bit vector. So that's the bracket C 0. From 3 down to 0, 0. Output, final output, C out. Y, internal Y. Because I have C out 0, C out 1, C out 2. Internal. Okay? And then we're going to call 4 instances. Just how we define. Okay? Right? 4 bit for item. A0, A1, A2, A3. And then map the order. Carry out, right? Carry out 0, and then S0, A0, B0, Ci. For this one. And this one, C out, S, A, C out 1, S1, A1, B1, C out. And F at 2, this one, F at A3. Done. Any question? Any question? I'm going to invite you. Follow this example. Can you design an 8-bit for item using this 4-bit item, ADD4? We designed it just now. Just call the instance. I'm going to challenge you, right? Okay. Step by step, we get a bigger circle. Would you like to help us? Okay. And everybody, I challenge you, I want you to give a try. Follow this example. And you just need 2 instances, right? From lower 4-bit go to higher 4-bit. Now, how many bits are your input output? 4 bits input, 4 bits output. Right? And then when you together combine together, you get 8 bits. So we are going to directly use this module called ADD4. We just need 2 ADD4. Maybe the practice is like this way, right? You design another 4-bit item. So this will be what? ADD4, right? ADD4B, and then you carry out, and the final carry out, and this is A to 0, B to 0. This is the original CI. Now you can give a name of this one. Maybe we call this one C out, final C out. This one. This is maybe C out. This one. 4. C out 8. How about this? The final in between will carry out, and finally we get a counter carry out. Right? Yeah. So in this way, we say that this is actually 1 bit, 4-bit input. 4-bit input. And together we say this one is a what? S. S A 3 down to 0. And this S7 down to 4. Right? And this may be what? A3 to 0. And A, right, 7 to A, B. Oh, this is A, this is B, right? This is A, this is B. This is A7 down to and this is B7 down to 4. Right, how we do this? So you are going to take one. Each A and B are 8 bits. 8 bits. Right? And then you're going to call this module. Right? Okay. So it's actually step by step we stack them together and then we get a bigger circle. Huh? Oh no, can you write the code, right? Okay. I sketched the architecture and we want you to write the code for it. We're going to call 2 instances and make the proper connections in between. How can we make the connections in between? We specify the port map. Because we assume each module either can take this let's say what 4-bit input, 4-bit input, 4-bit output, 4-bit output, or 4-bit output and 1 final output. And take a cavity. Yeah, each of you. Yeah, let's do it together. How can we use the instances to design a circuit based on the previous circuit you already designed. Can we call a instance? Can we call a instance? So your bigger block may be like this way. The bigger block, you are taking the A 7 down to 0, B 7 down to 0, and then you're going to take a carry in and generate a sum. We call the sum, right? Sum of S 7 down to 0, and generate final carry out. Carry out because carry out 8. We have a carry out 4. We as an intermediate carry out. We just call 2 instances, right? Okay, very nice. Okay, good. Very nice. Oh yeah, then we just need 2 instances. We just need 2 instances. Oh yeah, so yeah, either 4, yeah, you're right. And we give a name. Because there's what? Either for A, either for B. So either for, and we have the what? Either for A, either for B. And either for, yeah. So I think this is the original, either for is the original matter. And we call instant because either for A, for B, right? So for A. Very nice. Very nice. And then put it up. Okay. So this case here, I think ours is 7 to 0 for our model. 8 is very nice. And then we say also define wire. Wire is a combo. Now it's very easy for us to define, right? This is 4A. Or how about this? We said you are using the lower as a 4A and the higher as a 4A. Then in this way, 4A is the map is what? Follow the original diagram. Sum carry out CIAB. So yours will be a sum is actually what? S3 to S0, right? The lower 4 bits. Lower 4 bits, then let's say here. Yeah. This is a single bit, and then for ours, let's say here, right? This is A and B, A3 to A0, B3 to B4, right? So actually you say that A vector, A3 to 0, B3 to 0, and then your S3, oh no, here is sum first. So S3 B to 3 to B to 0, A B to 3 to B to 0, B to 3 to B to 0, and then your CI. Oh no, CI, right? So this one. So actually we call this one sum carry out. This one, and then this one. First, this one, and then this one A and this B. Oh no, CI. This is CI. So your order will be this one, and then this one, and then this one. And then the second one will be first this one. And then your CL. And then your CL4. And then A, and then so maybe we follow this one. It doesn't match the original. It's okay, right? Okay. Yes, yeah. And then this CL2, very nice. And then CI. And then A, B to C to B to 0. Yes. And then B, B to C to 0. Very nice, that's the first one. And then the second one is S is 7 to 4. And then C out of A. And then C out of 4. That's your CI. And then A B to 7 to B to 4. To B to 4. And then B to 7 to B to 4. Right? So I think now we have the two instances. And then in the module. Congratulations. Thank you so much. Right? Okay. Yeah, I'm so proud of you. Okay. Here there is a essay. Okay. Thank you so much, essay. Right? Okay, good. So I think essay did a fantastic job, right? That's how we do it. First, it's always helpful for us to sketch the block diagram and mark the names. And then follow this example we call two instances. And then exactly follow the same order as you declared here to match to our design. Okay, any question? Right? Good job. And if you have 8 bit, let's put at can you again stack them coincidence the design? Our Windows system is what now? How many? 64 bits, right? 64 bits, then can you design a 64 bit for item? Then we are going to call 8 instances. 8 to 64. You can quickly become just make a connection. Okay? Any question? Any question? What is it, right? How we define it. Now continuous assignment. So what we do is we can assign a value into a wire or a signal into a output form. So this is actually what we use an expression. Can be a conditional expression, true or false. It's true one, otherwise it's 0. And it can be an AND function. And it can be inverter. And it can be a addition. This is addition. If you want to OR, use OR. That's addition, right? So we can use mathematical and then assign the value to here. And even sometimes we didn't. So Y, this is the name of the Y. And you assign the inverter input the inversion into this INV after 10 units of delay. Right? And Y, you assign the value into this Y. This Y is a vector, P7 to P0. You are taking 8 bit input A and B, add them together, the value assigned to C. This one, the true or false, 1 or 0 assigned to Q. This is A and B assigned to out. Okay, right? So in this way, we can assign a value. And this is useful for what? Behavior model. Because behavior will just assign your Boolean function of your input to your output. Now let's see example design. Simple XOR gate. You will use a behavior model to design XOR gate. Previous with the primitive, we directly use it, right? But also we can use behavior. How do we behavior? This is the same. Module name, hot list, input, output, right? Output list. Okay. Now what are we going to do? Assign C equal to what? A X or no, this is X or B. We have this one. Bitwise not, bitwise and, bitwise or, bitwise XOR. You can use A, X or B, assign. Any question? That's behavior, right? Behavior. For either, we can also use behavior. Previously, we use primitive. Now we use behavior. How about we use behavior? You just figure out what's the function here. What's the function here? What's the function here? It's S assign. A X or B. A B X or C in. B X or C in to here, and then X or A. Just assign. assign, CL. This AB, BC, AC, right, assign to CL. It is okay? Any question? Any question? And this one, either 4, we can also assign. How? Input declaration, module name, import list, input output. Right? This is the 4 bits, bit C to bit 0. And then C output, right? 1 bit. And then assign. What are we gonna do? A plus B, this is not O. O usually is O. A plus B plus C. Assign to a combination of these 2 signals. So C out, higher bit, S is low. C out is 1 bit, S is 4 bit. Any question? So that's good? Right? Okay, so this is actually an example. Assign. Even more, we can make it more general. How about we want an n-bit item? N-bit item we can design private. We call this width. But initially we set the value to be 2. And if you want to change it to be n-bit item, just change this to be n. What are we gonna do? We are actually declare this item to be a n-bit. N-bit. The input of this one, input is this what? Bit 0 to bit width. For example, if width is 2, that's actually 3 bit. 3 bit input, 3 bit item. And output and here. Assign A plus B plus C go to the carry out joint with the sum. If we want a 10 bit for item, no, let's say what? How about this 8 bit for item? What should be the n number with it? What should be the number? 8 bit for item. 7, very good. 7. So it's bit 7 to bit 0. Good job, right? Good job. So you see that word. This is a more general design. You can easily change it to any bit. That's a good habit. Make your design more general. Okay, any question? So that's good? And this shows the here, right? Behavior model. The operators we can use are these. Right? Reduction or logic and logic or logic and. Logical equality, right? And not equal, but inequality. And less relational. And the others are modulars and so on and so forth. Right? Bitwise XOR, or. Those are the ones we can use. Okay, so this one shows here, right here. Now let's say here. Logical values. Typical logical value can be 0, 1, unknown, high interest. One is what values. And the unknown means that at this moment we don't know the value yet. For example, initial value of the sequence could be unknown, right? We don't know yet. Okay? But Z is different. Z is floating. Not connected to anywhere. That's a float. Okay? X, unknown. Verilog data type. The Verilog data type we have wire register. What's the difference? If we say it's a wire, it's an internal wire or other wire, it doesn't store the value. But if we define it as a register, it can hold the value. Because why register, right? You can remember the state. Okay, so anyway, this one anytime the wire only has one value. But this register type, it has a history. Right? You update the new state, you have previous current state. Okay? And then integers, the width of data. Right? And the format, the base. Decimal, binary, hex. The value. Okay? Array register 9 to 0. Right? What's the meaning? We're defining an array. It's a vector. Right? It's a register array. Okay? And from bit 9 to bit 0, 10 bit. the name is 1. Okay. Also, we have parameter. Just now we show you one parameter, right? You define a name of the parameter, then you can change the value to any value you want. Okay, so that. And the while and border size minus 1 to down to 0 of the bus. Preprocessor directives. Sometimes we allow you to define your own values. For example, a counter or whatever you want to count down the values or whatever, you can define, predefine a name and the initial value. Right? We allow you to define any value. So data type, we have names, registers, integers, array, parameter, preprocessor directive. Right? So you have different data types. Just like we have table, we have chairs, we have windows, right? These are the available components for us to build a house. These data types are the available data for us to use in VERILOG. Always block. Always block. Always block is actually what? Containing sequential statement. That's like a process in VHDL design. Right? Always we're going to do this. And then when we're going to trigger the always process to evaluate, we have a sensitivity list. So always add this sensitivity list, then we're going to do this. Sensitivity list is if any signal in the sensitivity list changes the value, then it's going to reactivate this always block to execute again, to re-evaluate the values for the outcome. Okay, so always add sensitivity. Sensitivity list can be label sensitive. Just include the names. Use O, A or B or C. If any of these A or B or C change the value, then we are going to re-evaluate the block. Always block. Otherwise, it's going to hold. That's what very reasonable, right? If we have a circle, okay. If we have a circle, if your input is not changing, then your output will remain correct, right? Only if your input changes, then I have to re-evaluate. Okay, so clear? Otherwise, I just stay the current value. This is called event. Sensitivity list, then we just be sensitive to this. Now, we can be sensitive to the value, the label. If the label changes, I'm going to re-evaluate. Or I can say, I'm sensitive to your age. For example, flip-flops, age trigger. Then we can use a positive age or negative age. So always add a positive age or clock. Always add a negative age or clock. Then we're going to do something. Okay, right? If or else the case statement, the branches, they are included in always block. We're going to show you what we can do with this. Right? So this shows the wire register, right? When you define the wires, when you define the register, right? These two types will result in different outcome. If you define it as a register, then you do the synthesis, you are going to see a register category. If it's a wire, then you just have a big wire connection in between. Okay? Right, so you see that one here. This one. If and the case statements, that's a conditional. If tomorrow is raining, I'm going to stay. If it's not raining, I'm going to New York City. That's a condition, the choice. Now we'll see the syntax like this way. If expression, condition, true or false. Okay, and if this expression begins at a statement, and else if another one, then do this. Else all the other conditions to this one. Yeah, that's a command. This is the example if statement. If what operation? ALU function. That's a modus direction. It's 2-bit. Right. So if is equal, conditional is true or false. Double equal. If this ALU function is 2-bit binary 0, 0, then I perform addition of A and B, send to ALU out. Assign, right? Else if this mode selection signal is 0, 1, we have to perform subtraction, send to output. Else if the mode selection, the function mode is 1, 0, then I have to perform a in the function, send to output. All others else, we like, for example, there's all other cases, then we use A or B, send to output. It's always a good habit to have a else, right? Because that is going to avoid potential missing cases. If you have any cases didn't list here, then you just stop here, you list 3 of them, actually you have 4 possible cases, then Alexa will be confused. Okay? So anyway, to avoid the confusion, all the else, all the other conditions, what you should do. Okay, so clear? That's if, right? Now case statement. Case statement. Case statement is very useful for us to write a sequential circuit, STG, state transition graph. So case, your current state. If it's in S0, what happened? If it's S1, what happened? S2, what happened? Case, case. So case. Now let's look at example case. Case expression, ALU control. If it's 0, 0, then perform addition, send to output. If it's 0, 1, perform subtraction, send to output. If it's 1, 0, perform AND, send to output. Default, that's the else. Default, other condition. Then we here we took this one, X. Unknown value. Because it doesn't kill state. Because in this way, we can get a minimum voltage generation. In the K-map, you can see the don't X, don't kill X. For other cases, actually it helps us to minimize the circuit. We can decide the value. Okay, now let's see here. How we're going to use this statement here, right? 4 adder design. Again, we like a 4 adder, right? We can see the 4 adder design. Okay? Declaration module name. Input, output. Register type. Some carry out. Right? That means it can remember the state. Every clock cycle, you're going to input 1 value, generate 1 output. Right, so we use buffer, right, buffer. Okay, the registers stored. Okay, always wrong. Either sensitivity is A, B, or C, A or B. Any input change, we're going to reevaluate. We're going to define it as they're always wrong. What are we going to do? Sequential statement. Sum is A XOR B XOR C. Carry out is A and B, or A and C, or B and C. Okay, so is this okay? So it is what we defined in A1. In an always block. In always a block is a sequential statement. It's usually 1 by 1. And this is like the process in VHDL. For example, in the class, we have homework 1. Homework 2, homework 3, homework 4. Sequentially, we group them in a block, always block, with a sensitivity, right, of the input. How can we design a 2 by 1 mux? I see you are doing this in the lab projects, right? Mux, 2 by 1 mux. How should we do it? We have choices. We are going to use the A1. Either directly assignment in your module, or we use always block. If we use always block, we can use if then, or we can use case. Okay, now we try all of them. Assign A is equal to 1. What is it? Select question mark B or C. That means it depends on this condition, true or false. True or false. If it's true, select this one, go to A. If it's false, select this one, go to A. See, that's a conditional statement. Right? If this one is true or false, either choose A or B or C, go to A. Now, always block. Select, always act. Sensitivity list. Either this one, any input change, output is going to change. Okay, right? Now, if you select the 1, A equal B assigned to A. B assigned. Else, C assigned to A. Right? That's it. Now, always using the case statement. Case select. If the 1, right, B go to A. If the 0, C go to A. Okay, any question?
Any the question mark in the first part?
Question mark, that's let's walk. Another way to write a conditional statement. Okay, so this is actually the condition, true or false. If it's a true, take this value. If it's a false, take this value. And then go to the signed output. So this is actually a conditional statement. Choose either this or this value, depending on this condition. True or false. True or false. Any question? So far, so good? I'm going to challenge you, right? Okay. Using this one. Using this one. Okay. This is actually what? Let me see the 4 item. 4 item. Case. Right, case. AB. 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 Okay, so let's say here. A, B, C, and then what the sum, the carol, sum, right? Sum. This is actually showing the here, right? Or is it here? If this is actually 2 to 1 marks, can you design? This is not in Shannon's extension. 4 to 1. A, B, C, D, out. 0, 0, 0, 1, 1, 0, 1, 1. S, E, L, beta 1 to beta 0. How are we going to do this design? Right? How do we do this? Can you track each of them? Each of them. Okay? So for this one, you say if the 0, 0, what happened? 0, 1, what happened? Selection, right? 1, 0, what happened? 1, 1, what happened? Case selection. If the 0, 0, what happened? 0, 1, what happened? 1, 0, what happened? 1, 1, what happened? Right? But this one, I think you need to actually what? Use a combination of these two sentences. Right, two is the condition. That's the statement, right? Okay, so I challenge you. You will try. You will have 2 to 1 marks. 1, 2, 3 choices. How do we do that? 4 to 1 marks. Conditional statement. D marks design. 1 input, either go to here or here, using the special name. Right? What you would design? D same. Module name, import list, all the block, IT, sensitivity list. Begin. What are we going to do? If then, right? If selection is 0, then the D go to Y0, 0 go to Y1. Y1. So if it's 0, this one will be 0. Else, that means selection 1. Then what happened? D go to Y1. Y0 will be 0. It is okay? Right, the D mark. ALU using the case set. Sensitivity list. Right? So selection bit, select mode. 0, 0, perform addition, go to 1. 0, 1, perform subtraction, go to 1. 1, 0, increment by 1, go to 1. 1, 1, decrement 1, go to 1. That's the ALU. Any question? And another logic unit, like the ALU, right? You're going to decide the selection mode is a 3 bit. It will allow you to choose 8 votes. Each mode, what function is default or other case setting to 0. Okay? Now we are ready to talk about sequential circuit design, right? Mini machine, more machine. How we can write the code. And we have a template as well. In the sequential circuit design, we are going to mainly have these 3 modules. 3 modules right here. So we said that what? This is a example mini machine module. Current state. And oh no, this one here, right? This one. Oh, this is next state. This is current state. This is input, output. Depends on both input and current state. Go to F2. And this F1, using the current state and the input, decide the next state. Okay. So we divide into 3 blocks. Register block. Transition block describes the STT. Output decides your final output function. This is reset. Transition description of your STT. General output. It is okay? That will completely describe this sequential circuit. Reset, initially you need to reset. But if it's a more circuit, similar. Initial reset. If reset is 1, then you reset it to 0. Otherwise, keep it current state. Let's go next step, right? Next step in the protocol page. So it's a reset or past state, next step to the current state. Description of the STT. But the output only depends on state. More machine. Mini machine. Output depends on both current state and your what? Input and current. That's the mini machine. I'm going to use this as an example. What is this? STG. If we have this STG, 1 bit input, 2 bit output. Initial reset to X0. Now, how are we going to design the VERILOG code? This is the one. Right? See? Declaration module, FSMPX. Input output list, port list, definition. Output is 2 bit. We define this as a register sequence. Current state, next state, and out, often on 2 bit. State assignment. We need to do the state assignment. This is state assignment. Because this one's later state, you need to assign the binary code to it. 00, 01, 10, 11. State assignment. Now, either initial reset or pass the next state to current state when you have a clock right it comes. Okay, right? So in this way, tomorrow becomes today. Right? So this way, this one. Always either positive 8 or positive 8 reset. If reset is activated, reset the S0. Otherwise, in this clock positive 8, next state has current state. That's the reset and the state. Right? transition. Now, here, always this one, right? Okay, and another always block, we are going to use the C always blocks. Always a block for the reset and the state transition. Always a block for the STG description, and always a block for output generation. Done. Right? So in this way, see this one, description. Using the current state or input, trigger this always block. Case current state. If in S0, if input is 1, then go to S1, next state. Else, go to S2, next state. Input is S1, if input is 1, go S2, go to S2 state. Else, go to S1 state. That's the definition or description of your STG. Now, what happens if you current state is S2, then next state. Current state is S3, now next always go to S0. Or other cases, go to S0 to be safe. And that's the STG description. And then last one, output generation, using another block. What is it? Case current state. Because it depends on both the current state and input. Now, case state is S0. If input is 1, then what's your output? Else, what's your output? Input is state is S1. If input is 1, what's your output? Else, input is 0. What's your output? S2, output is always 1 0. S3, output is always 1 0. Right? Default or other case, set it to 0 0. Okay. Done. Right? So you see the whole procedure, just like our sequential signal design. We follow 1, 2, 3, 4, 5. What's the step here? What's the step here? 1, 2, 3, 4. Step number 1, state assignment. Step number 2, reset, and the state transition. Step number 3, STG description. Step number 4 is what? Output generation. Okay, if we get this, all this here, right? The 4 steps, we are done with the sequence selector. Okay, so this is we use 3 blocks, all the blocks for this 3. And then the first assignment, state assignment is the primary. Now, follow this template. Can you design the sequence detector we introduced to you in the last class? Both the reading machine and more machine into VERILOG code. I leave this for your practice. So next class, we're going to invite you to it. And this updated slides, I'm going to upload this to the canvas so you can use it. Okay, good job. All right, good job. Thank you very much.